Let us start explaining the notion of curvature. If we were to assign a number that represents the curvature of a circle, it is evident that we should give a bigger number to the smaller circle. We define the curvature of a circle of radius r to be 1 over r. For a general curve, we notice that some parts have more curvature than others. For this reason, it is natural to define the curvature of the point in the curve and not the curvature of the whole curve. We define the curvature at a particular point to be the curvature of the circle that best fits the curve near that point. We can give a sign to the curvature by defining a Gauss map, which is simply a choice of a normal vector to the curve. We say that the curvature is positive if the center of the circle that best fits the curve is in the direction of the Gauss map. Otherwise, we say that the curvature is negative. We can define the mean curvature in the following way. First, we define a Gauss map. Then, we pick a pair of tangent directions to the surface that are perpendicular to each other. Each tangent direction, along with the normal vector, defines a plane that intersects the surface on a curve. Since this curve lives in a plane, we can consider its curvature. The average of the curvature of the two curves is called the mean curvature. Helicoidal surfaces are foliated by helices with the same axis of symmetry. Up to the rotation, the intersection of a helicoidal surface with a plane perpendicular to the axis of symmetry is the same, and it is called the profile curve of the helicoidal surface. For a given helicoidal surface, we denote by capital R the distance from a point in the surface to the axis of symmetry. We will study helicoidal surfaces that satisfy this equation. These surfaces represent the boundary of a drop that is rotating about an axis. This is the system of ordinary differential equations that we need to solve in order to find solutions of the rotating drop equation. This theorem shows how to integrate the system. In order to provide an interpretation of this theorem, we defined the TreadmillSled operator. This operator takes regular curves to curves. This is the definition in words. The TreadmillSled of the red curve is the blue curve. These images shows a dynamical interpretation of how the red curve produces its TreadmillSled. Here is a solution of the rotating drop equation. If we define G in this way, we get that the profile curve of a helicoidal surface satisfies the rotational drop equation if and only if its TreadmillSled is contained in the level set of the function G. This polynomial will help us to understand all the level sets of G. From this parametrization, we get that we need to classify all the roots of the polynomial P. The following images shows the relation between the polynomial P and the level set of G. In most of the cases, the level set contains a regular closed curve. For example, this is the case when the polynomial is somewhere positive and all its roots are simple. For these parameters of C, A, and lambda, we can define the fundamental piece of the profile curve as the smallest connected part of the profile curve whose TreadmillSled is the closed regular level set of G. This image shows a profile curve made out of two fundamental pieces. In general, we don't have closed profile curves. Most of the solutions are dense in the region bounded by two concentric cylinders. When the polynomial P has roots with multiplicity or more than two roots, it defines several profile curves that are solution of the rotating drop equation. For some particular values of the parameters C, A, and lambda, these images shows the polynomial, the level set of G, and the profile curves that solve the rotating drop equation. This is the Moduli space of all solutions of the rotating drop equation with lambda equal 1 and non-zero A. The blue points represent a circular cylinder. The gray points represent a single non-circular cylinder. The red points represent a circular cylinder and a non-circular cylinder. The yellow points represent two non-circular cylinders. The green points represent a circular cylinder and two solutions with profile curves that converges to a circle.